Okay, so now we're going to go on to some of the important properties that allow us to simplify our calculation of Fourier transforms. The first is linearity or superposition. And this is exactly like we had before for systems, but now we're talking about signals. Effectively, what we're saying here is that the Fourier transform, the operation known as the Fourier transform, is linear. So if we know two or more Fourier transforms already, then superposition applies. That is to say, any scaled and added versions of those signals just gives us scaled and added Fourier transforms. And we can take a look at the proof by taking a look at the left-hand side, just taking the Fourier transform, separating those two because we just have an addition, pulling out the constants, and then these are just by definition x1 and x2. Duality. Duality is one of these ones that students often have trouble understanding, but is actually one of the most important ones and powerful ones. And what it is saying is that if we know one Fourier transform pair, so we have some function with functional form small x of t related to some other function capital X, in this case of omega, this implies that there is another Fourier transform pair that falls out of it. Notice that the capital X is over here and the small x is over here now, but the variables are staying in the same domain. So remember that little x and capital X are actually two different functional forms. So for instance, for the square pulse, in the time domain we had a square pulse, in the frequency domain we had a sinc function. So this second one would be, in the time domain we have a sinc function, in the frequency domain we have a square pulse. That's what it's actually saying. So it just says that if we know one Fourier transform pair, then we automatically know another one. I'm not going to go through this proof in detail, but if you'd like to take a look at it, there it is. But you're going to get lots of practice with this in the worksheets. Okay, symmetry. This is just something that's nice to know because it gives you some information going into a calculation. So there's actually two parts to symmetry. First is that if your original signal x of t is strictly real valued, then that means its Fourier transform is conjugate symmetric. In other words, it is even, the Fourier transform is even, but because it's complex valued, we also have to throw in that conjugation in there. So it's not even per se, it's what's called conjugate symmetric. And here's a proof of it. So I'm just taking the left-hand side, replacing it with its Fourier transform, conjugated, distributing the conjugation, but we know that x is strictly real, so we can replace this with just x of t, and then that gives us x of minus omega. In other words, a flipped version of the Fourier transform. If x of t is strictly imaginary, then you end up with a Fourier transform that is conjugate anti-symmetric, and is a very similar proof for that one as well. Now, it's sort of strange to think about an imaginary x of t. We usually deal with strictly real ones. However, just like complex numbers give us a way of analyzing things even though we come up and only consider the real numbers at the end of the day, it's the same thing with signals. Even and odd signals. If x of t is strictly real valued and is also only even, or an even signal, so in other words, if x of t is real and has even symmetry, then all of its then there is no imaginary part to its Fourier transform. It is strictly real valued Fourier transform. And here's a proof for it. I'm not going to go through the details. Conversely, if x of t is strictly real valued and an odd signal, then it has no real part to its Fourier transform. It is strictly imaginary. And again, here's a proof for it. Now, these might seem a little esoteric, but it does give us a little bit of a check on our work. So if you take a look at a signal, x of t, and it is an even signal, and then you're asked to calculate the Fourier transform, if you end up with an answer which gives you imaginary parts to the Fourier transform, then you've done something wrong. So it's a way of checking on things. Okay, time shifting. So if you know a Fourier transform pair, x of t goes to x of omega, x of t goes to x of omega, then if we now put a time shift on the signal, then the Fourier transform of that time shifted signal is given by this. This should make intuitive sense, but let's take a look at this. So if we take the Fourier transform of that time shifted signal, stick it straight into the definition, now I'm going to let lambda equal t minus tau. So that becomes x of lambda. This exponential becomes with t replaced by lambda plus tau, and dt becomes d lambda. But now I have an e to the minus j omega tau, and tau is not the integration variable here, so I can pull it out. And now this is just the Fourier transform of x of t. So we end up with this. Now that makes intuitive sense, because what it is saying is that if I do a time delay on the signal, that should be represented by a phase shift. So a time shift implies a phase shift in the spectrum. And note that that phase shift is linear with frequency. Okay, so now what if we do a frequency shift? So here what we're doing, you're effectively getting this from duality, but rather than doing a shift on the time variable, let's do a shift on the frequency variable. What does that represent? Well, we end up with our original signal, but now it's multiplied by e to the j omega naught t. So that could be found using duality, or if you take a look at the left-hand side and just do the Fourier transform of that, then that is just going to give you x at omega minus omega naught. Okay, because effectively this is the new variable, which is our definition of the Fourier transform. And this is the fundamental basis behind amplitude modulation. So it's an extremely important concept that's used in all sorts of different systems, from your phone to your computer to radar, sonar, and all sorts of different things. And I've just given, so remember that that exponential, we can use that to construct a cosine and a sine. And if we do that, then this would give you the Fourier transforms of those modulated signals. And note that it is just the original spectrum shifted to a higher and lower frequency, or copies of the original spectrum shifted to higher and lower frequencies. Now let's think about time scaling. So if we have our original transform pair, a time scale on the signal implies an inverse frequency scale on the Fourier transform. Take a look at the proof of that. So we're just going to replace AT with lambda. And if you do that, you have to do all these different substitutions. If A is greater than 0, then I'm still going from minus infinity to infinity. But if A is less than 0, then I'm actually going from infinity to minus infinity, because you have to change the limits for from t to lambda. But you will get the same answer from those, except for you have to take care of that absolute value. So notice that you get a frequency scaling, which is 1 over a. All this is saying is that if you do time compression, then that will lead to frequency expansion of the spectrum, and vice versa. This makes intuitive sense because time, which is measured in seconds, and frequency, which is measured in 1 over seconds, are the inverse of each other. So if I am compressing time, then I should be expanding frequency, and vice versa. Okay, differentiation. So if we have a Fourier transform pair, and we want to know what's the Fourier transform of the differentiation of that original signal, then it's just represented like this, or it's defined like this. Think Laplace transform. You've actually been doing this since your math class last semester. If you just replace j omega with s, then you can see that this is exactly what you're doing when you do a Laplace transform. And we'll talk a little bit more, quite a bit later on, about Laplace transform versus Fourier transform. So let's take a look at the proof of this. So we just replace x with its inverse Fourier transform, and then I reverse the order of integration and differentiation because they're two different variables. And if I do the differentiation, I only get the j omega, and so that gives us, if I do one derivative, I just get a single j omega. And you can just keep repeating this process. If you just take a derivative of that result, you just get another j omega and another j omega, etc. What if we do differentiation in the frequency domain? Again, you could find this from duality, or we can go straight to the proof. We're going to take a look at the right-hand side, and it's effectively the same thing we just did, on the last slide. So we've reversed integration to differentiation. In this case, we actually get a minus jt. And then if you repeat the process, you get minus j to the exponent n. Like I said, you could also have found that from duality. Okay, convolution. Remember how we spent almost an entire week on convolution and shifting and scaling and cases, etc., etc., etc. And like I said, you can expect that there's going to be a way easier way to do this. Well, this is how we do this. This is probably one of the most important ones, especially for a student, because this simplifies your work greatly. If we know two Fourier transform pairs, it can be shown that the following two properties apply. The first is, if I take a convolution in the time domain, that just means multiplication in the frequency domain. If I do convolution in the frequency domain, then that just means multiplication in the time domain. In other words, convolution in one domain just means multiplication in the other. The only thing you have to watch out for is this 1 over 2 pi. And here's a proof of the first one anyway. I am directly putting in the definition of convolution into the Fourier transform. And then I am reversing the order of the time differentiation and the lambda differentiation. Remember, those are just dummy variables which we're integrating out anyway. And then that second one just becomes x2 of omega. By definition, that's just the Fourier transform. And then that what's left becomes just the Fourier transform of x1. So I end up with just that multiplication. Okay, this is going to have huge implications on our methodology for analyzing linear time invariant systems. That's going to be the next section of the course, but let's just give a hint of it right now. So previously, if we wanted to figure out what's the output of a system, if the input is x of t and I found the impulse response, I had to do a convolution. And we all know how messy that could be. Well, now what we're saying is that in the frequency domain, I can represent that whole thing in a completely different way, not a completely different way, but in a very similar way, where the signal in the frequency domain, if it now goes into this system, I can find the output by simply multiplying the Fourier transform of the input with the Fourier transform of the impulse response. Now think about what that means. So you could do it the probably more difficult way, and that is to, if I want to find the output, I'm going to just do a convolution of the impulse response h of t with the input x of t. But now we have an alternative. Rather than taking that short but difficult path, I can take the original input and find the Fourier transform. I can find the impulse response and find its Fourier transform. Then I just find the output via multiplication, and then do an inverse Fourier transform to find what that output is in the time domain. Now, it may seem like a longer path, but it might actually be quite a bit easier because you don't have to do a convolution. Here, on the red path, the difficulty is actually calculating the convolution. On the blue path, the difficulty is finding the Fourier transforms of x and h. However, there are tables of a lot of different functions for finding that, and then you can use the properties to find them for other ones, or variants of those. I like to think of an analogy where, say I'm on this side of the mountains and I want to get over to the other side of the mountains. What are my options? Well, I could take the really hard path, which is climb to the top of the mountain, climb back down the other side. That might be shorter, but might also be way more difficult. Or I can walk along until I find a nice mountain pass, which is actually really easy to get over, and end up at the same spot. So it might seem like a longer path, but it might actually take way less work. That's the way I like to think of thinking about things in the frequency domain and analyzing systems. In summary, so this is where the gift comes. I've given you a few examples of a couple, not all of these, but some of these signals and their Fourier transforms. And we can list a few more of those. And then we also have a bunch of properties that we can use. And the combination of those two actually allows you to find quite a number of Fourier transforms of signals. And you're probably already doing this with Laplace transform tables. Now you're going to be doing them with Fourier transform tables. And you will be given these. You will not have to worry about memorizing any of these. You'll see in the worksheets that you're going to be working with two tables which are very similar to these, and you're going to be using these throughout the rest of the semester to take a look at Fourier transforms and for analyzing signals in the frequency domain. Okay, that's it for now.